In this tutorial, we will be discussing the concentration calculations with KSP and the effects of pH. And the first type of problems that we've discussed with KSP, we've been calculating KSP given the concentration or the molarity of the products. This time we're going to be discussing the calculating of the solubility concentrations of the products when you're given the KSP. Predicting the solubility of the concentrations required to have the precipitation when given the KSP, and the common ion effect on precipitation reactions when given KSP. So let's just jump right in. Calculate the molar solubility of lead chloride in pure water at 25 degrees Celsius given the KSP of 1.17 times 10 to the negative 5. First thing we want to do is figure out what the equation is. So PbCl2 breaks down to Pb2 plus and 2Cl minus. So that means if we initially have zeros here, you're going to add X for the lead, and because of that coefficient of 2, we're going to add 2X for the chlorine, which means Pb2 plus is X and chlorine is 2X. Now we turn around and we plug this back into the KSP equation. So 1.17 times 10 to the negative 5 is equal to X for the Pb2 plus and then 2X for the chlorine. And we're going to square that once again because of that 2 in front. So this becomes 4X squared. So that means 1.17 times 10 to the negative 5 is equal to 4x squared times x is 4x cubed. Now we want to look for x. Divide both sides by 4 and then take this cubed root. (1.43) times 10 to the negative 2. Now we want to plug that number back into our concentrations. So that means Pb2 plus is going to equal just plain 1.43 times 10 to the negative 2. Whereas Cl minus concentration is going to be 2 times that. Which comes out to be 2.86 times 10 to the negative 2. Let's try another one. This time it's a little bit different. Last time we were trying to figure out the concentrations at equilibrium. This time they've given you the concentration. So we're going to skip the ice table altogether. So the KSP is equal to the mercury. We have 2 chlorines, so Cl minus squared. So that means 1.1 times 10 to the negative 18 is equal to mercury, which we know is 0.01, times x squared, and x being chlorine. Divide and take the square root, and we find that we need 1.05 times 10 to the negative 8 to make a precipitate. Now it actually says to just begin, so we need right at that amount or lower. So let's talk about the common ion effect on solubility. The addition of the soluble salt that contains one of the ions of an insoluble salt decreases the solubility of the insoluble salt. For instance, the addition of sodium chloride on the solubility equilibrium of solid lead chloride decreases the solubility of lead chloride. You're increasing the amount of chlorine with the NaCl. As a result, because of Le Chatelier's principle, it's going to shift to the left, therefore decreasing the solubility. Alright, so now we're going to determine the molar solubility of calcium fluoride in 0.1 molar NaF. So we already have some fluorine in there. Alright, so first of all, let's get our equation going. CaF2, Ca2 plus 2F minus. Initially, we don't have any calcium in there, but evidently we already have 0.100 molar of the fluorine. When it reacts, we're going to add X on the left-hand side, or on the calcium. For fluorine, because of the coefficient of 2, we're going to be adding 2X. So that's going to be X in 0.1 plus 2X. We're now going to put this into the equilibrium equation, into the KSP. So we have X times 0.100 plus 2X. We have it squared, because of that coefficient, is equal to 1.46 times 10 to the negative 10. Now, because we're assuming that this 2x is going to be far, far smaller than 0.1, we're going to get rid of it. So that means we have 0.100 squared times x is equal to 1.46 times 10 to the negative 10. So we square the 0.1 still, and that comes out to be 0.01. Divide both sides by 0.01. X comes out to be 1.46 times 10 to the negative 8. Alright, so now we're going to turn around and we're going to plug it into these equations up here, so that way we can figure out the actual molar solubility. For calcium, it's simply going to be what X is. For fluorine, that's going to be 0.100 plus 2 times 1.46 times 10 to the negative 8. That value is so small that it comes out to be approximately back to 0.100. Let's try another one. Determine the concentration of silver ions in seawater that have a chlorine concentration of 0.55. So originally we have no silver in there. We're going to add it. AgCl is what we're trying to get. That's Ag plus and Cl minus. So I don't have to worry about any coefficients here this time. Plus X. So that's X 0.55 plus X. Once again, we're going to assume that this X here is so much smaller than the 0.55 that's insignificant. So that means 1.77 times 10 to the negative 10 is equal to X times 0.55. Divide it out, and we have X is equal to 3.2 times 10 to the negative 10. So determine the concentration of silver ions. That would be the concentration. Alright, so let's change gears a little bit and start talking about pH. The pH of a solution may have an effect on the solubility. For instance, if it's an insoluble hydroxides, the higher the pH, the lower the molar solubility of the hydroxide ion in solution. Remember that the increase in pH results in an increase of hydroxide ions there to begin with. Therefore, the solubility ends up decreasing. They take less hydroxide ions present in solution for the precipitation to happen. you need fewer hydroxide, so the solubility decreases. If you lower the pH, the higher the molar solubility increases of the hydroxide ion in solution. The solubility increases because of the fact that the OH and the H from the higher concentration of hydrogen are reacting. There is not enough OH present in the solution for the precipitation to occur. So the lower the pH means that there's greater numbers of H+, which means that'll balance out that hydroxide. So that means that more can dissolve. For insoluble ionic compounds that contain anions of weak acids, the lower the pH, the higher the solubility. The lower pH means that there's a higher solubility, means greater hydrogen content in the solution. The hydrogen reacts with the basic anions to produce water, causes an anion to decrease. So the hydrogen starts reacting with the anions here, as you can see right here. Alright, so let's try to put this into effect. Determine if each compound is more soluble in an acidic solution than in a neutral solution. Alright, so let's first take a look at barium fluoride. The solution of barium fluoride will be greater in acidic solution because the fluorine ion is a weak base. So therefore that fluorine is going to absorb some of the hydrogen, and therefore it's going to dissolve more. Silver iodide, the solubility of silver iodide will not be greater in acidic solution because iodine is not a base. I- is the conjugate base of a strong acid, Hi. Once that hydrogen leaves iodine, it doesn't want it back. So therefore it's not going to pull anything else out of solution. And finally, calcium hydroxide. The solubility of calcium hydroxide will be greater in acidic solution because of the hydrogen, because the OH minus ion is a strong base. So therefore that OH is going to absorb that hydrogen. And that is KSP and pH.